take the easy way. Welcome to the Invisible World, the show that gives you a chance to see who creates the things we use every day but we take for granted. Like who makes sure we have safe water to drink, that our computers work right, that our buildings don't fall down. Well, in fact, inside this school today, somebody's going to find out all about the invisible world.
Okay, we've only got a couple of minutes left. Now is the time you've been waiting for. You've all had 3 months to do your projects, and I guess tomorrow is when we're going to start looking at them. What do you think? Okay, so does anybody want to go first? Chad, you always go first. Let's give someone else a chance this time. Anybody else? Huh? Anyone? I didn't think so. So I took the liberty of putting all of your names into this hat, and we're going to draw out the name to see who will go first tomorrow.
Please not me. Please not me.
And I'll pick out the name. Whoever I pick gets to be the first one to go.
Pick me. Pick me.
And the winner is Brianna. Okay, well, I'm looking forward to your project, Brianna, because I remember last time you did a great one. It was really good. And weren't you going to do this time a popsicle bridge to show form and structure of a bridge? How's that coming?
Well, I'm having a little trouble with the bridge, and if I could have a couple more days,
You've had 3 months!
I'm sure what you've got's fine. We'll just take a look at it tomorrow. As for the rest of you, I guess that's it. Thanks a lot.
I'm so busted.
Brianna is so busted. You know, I'm not the smartest guy in the world. I'm third smartest. But it looks to me like Brianna hasn't even started her popsicle bridge. It probably would help her if she knew who designs bridges. Or for that matter, roads, stadiums, skyscrapers, reservoirs. Who makes sure they work right and they're safe? I'm waiting. Oh, actually, I know. It's engineers. No, not the train guys. A fine profession. But I'm talking about the engineers who get to solve all our really hard puzzles every day. Like, how do you make a skyscraper 800 feet tall that won't crumble in an earthquake? How do 75,000 screaming football fans pound their feet during the game and the stadium doesn't collapse? How do 2 300-pound wrestlers repeatedly punch each other and nobody gets a bloody nose? Wait a minute, that's not engineering. I'd still like to know. Anyway, my point is, there are civil engineers, structural engineers, mechanical engineers, electrical, environmental, geotechnical, transportation, hazardous waste, solar, hydrology, planning, acoustical, industrial, illumination. I hate it when I do that. Anyway, those are the people Brianna could use right now.
Why did I pick a popsicle bridge? Can't build a popsicle bridge in a day. I don't even know where to start. I don't even know where to get the popsicle sticks. It's a sign. I've got to make a phone call.
Try to answer this question. Do you know why armies don't march across bridges? Why can't armies march across bridges? Because in 1850, a 500-man French army troop marched in step across a suspension bridge and vibrated it so badly that they fell into the water below.
That's why they call stomping in unison river dance. All right, let's move on. All right, here's our challenge. I need to figure out how to go from here over this river to here. But what if you don't have fancy camera tricks? Then you're definitely gonna need a bridge. But what kind of bridge? How long is it gonna be? Or what's the span? What kind of traffic is gonna go across it? To answer these questions, I'm definitely gonna need a consulting engineer.
Hi, my name is Taka Kimura and I design bridges. You know, there's a lot of reasons why I became an engineer. I really love the job. I get to design big structures like this. There's a lot of ways I get involved in the life of a bridge. First of all, there's the design, of course, and there are a lot of things to consider. What kind of material you're going to make it out of? Wood, steel, and sometimes they even make them out of plastic. But once you've figured that out, you have to figure out, well, what kind of bridge are you going to use? Are you going to use a suspension bridge, truss bridge? You wouldn't use a suspension bridge for a little creek, and you wouldn't use a little footbridge for a mile-long bridge. Now, there are a lot of other engineers that are involved in the design of a bridge, but between you and me, I'm the most important one, because without me, there would be no bridge. And another thing about these bridges is, oh wait, hold on a second. I think it's a client. Hello, Taka speaking. Hey Brianna, how's it going? You want to build what?
I want to build a popsicle bridge, and I have no idea how to do it. It has to be done by tomorrow. My budget's like $8. Can you help me, please, please? Oh, thank you. Now, what do I need? I'm glad I didn't have lunch.
You didn't eat all those popsicles, did you?
Mom, I need to build my bridge.
Honey, they sell them at the craft store. I already bought you a box.
Now you tell me.
Hi, I'm Daria Drago. I'm a civil engineer who specializes in hydrology. My favorite reason for building a bridge is to cross water. The water dictates some of the characteristics of the bridge when we cross it. I think I'm the most important engineer on the design team, because if you don't take into consideration what the water is going to do, it won't be long before you don't have a bridge left at all. The volume of water going through we determine using something called a 100-year event. It's a flood that has a 1% chance of occurring in any given year. If we build the bridge too low and we don't know that, then the water can overtop, washing whatever happens to be on it away. Another concern is something called scouring. It's when floodwaters become very turbulent and they erode the foundation of the bridge, sometimes causing it to collapse.
Do you know how many bridges there are in the U.S.? Here's a clue. They only count bridges over 20 feet long. I hope that helps. How many bridges are in the United States? There are 582,984 working bridges in the U.S.
582,984 working bridges. What do they mean working? Do they tell us which ones aren't working? Is this one okay? Well, we've found out that there are a lot of working bridges. So now let's find out what kind of bridges there are so we can determine whether they're working or not. One type of bridge is a suspension bridge, like the well-known Golden Gate Bridge in San Francisco. Still looking nice today, even though it opened for traffic in 1937. There are also arch bridges that look like this bridge over the Hoover Dam. When was this one built? It hasn't been. This is a computer-generated bridge consulting engineers created to show what their bridge might look like when finished. This beauty is a cable-stayed bridge. It's the Sunshine Skyway Bridge in Florida. It was built to replace a pre-existing bridge. There are elevated bridges like the ones used in the Glenwood Canyon Bridge Project, the most extensive bridge project in the United States, where 40 bridges were built over an 11-mile distance. There are many other types of bridges. There are truss bridges like this one, there are concrete segmented bridges, and in television there's the Segway, which is a bridge from what I'm saying to this person.
Hi, my name is Scott Sonart, and I'm a geotechnical engineer. What my job is to basically design the support system for this beast of a bridge you're looking at here. We've got to dig down past all this dirt and the sand that you see here. We've got to dig down to get to the bedrock, which is the actual earth that the bridge and the foundation will be attached to. The piers need to be designed underground, twice the height of the bridge. So most of the bridge that you're looking at is actually underground. It's great to work outside, and it's also exciting to watch structures go up utilizing the Earth's natural resources. Without me, the bridge may collapse or it may also float down the river.
In 1969, the Golden Gate Bridge needed to be sandblasted, treated, and repainted. What year did they finish? What year did they finish sandblasting, treating, and repainting the Golden Gate Bridge? 1996.
Wow, 27 years. Maybe they should use aluminum siding. Anyway, how do bridges work? What makes them so strong that they can carry all that weight? Well, the point of any bridge is to channel all the weight on the bridge back to the ground. Each bridge does it a little bit differently. For example, an arch bridge uses compression. Compression makes an arch bridge strong because the weight on the bridge is spread across every square inch of the bridge equally and evenly. I'm about to show you an amazing arch structure, one that can withstand forces many times its own weight. It can withstand pressures more than you can imagine. Of course, I'm talking about an egg. Obviously, eggs are incredibly fragile things, but they have this arch form which makes them incredibly strong. Try this experiment, if you dare. Take the egg, put it in your palm the long way, and squeeze as hard as you can. Now, I'm not the strongest man in the world, I'm third strongest, but the egg is defeating me using compression.
Are you too weak to crack an egg? Then eat these. New eggs in a box. They have no fat, no cholesterol, but no structure.
My name is David Simpson. I'm a civil engineer who works on transportation projects. I'm the most important engineer on the design team. It is my job to look at different alternatives and to find the best fit, so to speak, for the bridge that you see behind me. Without me, the bridge would not have a home. I determine where the bridge is to be located. All activity must come through me. Traffic engineering, roadway design, bridge design, hydraulic design, right-of-way, all of those design activities must come through me. I'm the most important person on the design team.
Now, you may think that an arch bridge looks like an upside-down suspension bridge, and if you thought that, you're right. But a suspension bridge uses the opposite of compression. It uses tension. So instead of pushing the weight back to the ground, the weight of the bridge is pulled back to the ground. In fact, each main cable on the Golden Gate Bridge uses 81,000 miles of wrapped wire to stop it from falling into the water. That would wrap 3 times around the Earth. Other types of bridges use a combination of tension and compression. But how do consulting engineers know how a certain bridge will look or if it'll fit a given location? The answer is experience and computers. As consulting engineers prepare a bridge design for cities, an important tool they use is to design the bridge with computer graphics to show what it will look like after it's complete. Here are some choices given for a bridge that will span the Hoover Dam. Which one do you like best? What kind of things would you like to show if you were a consulting engineer? Maybe you'd show what it would be like to add a second bridge for more lanes of traffic. You might want to show what it's like to drive across the different types of bridges you can design, in both directions. Or maybe you would like to say, ladies and gentlemen, here it is, I have designed your new stadium.
I'm Nancy Clanton, and I'm an illumination engineer. That's the type of engineer that does lighting design. I'm responsible for doing the roadway lighting and for the pedestrian lighting across a bridge. I love being an engineer because I get to create with light. It's almost like being an artist and being able to paint structures with light. I'm the most important engineer on the project because if the bridges weren't lighted, then no one could see their way across the bridge at night and could fall off.
You can use computers for bridge design, but what about safety and testing? I mean, you can plan on cars or rain, but what about the local terrain or high winds, tornadoes, earthquakes? Earthquake! Anytime a bridge is built, local phenomena has to be taken into account. This computer simulation is showing what would happen to a bridge in an earthquake area. It has been designed to sway back and forth during an earthquake instead of shake. Even though all bridges are tested thoroughly, sometimes Mother Nature and a little bad luck can cause a lot of problems. This is the Tacoma Narrows Bridge, the pride and joy of bridge builders in 1940. People came from miles around to drive or walk on Galloping Gertie, which would sway and move with the winds as it blew across the bridge. As a team of engineers worked on the 4-month-old bridge to learn how to stabilize it, civil engineer Professor Farquhar took movie footage when the winds blew at different speeds. On November 7, 1940, at 10 a.m., a 42-mile-an-hour wind hit the swaying bridge at the wrong angle and the bridge began to oscillate. Drivers and pedestrians hurried to get off the bridge. Not an easy accomplishment, as this man can attest. The bridge, now clear of people, continued to pitch back and forth while engineers worked furiously to determine how to correct the problem. After 45 minutes, the main span of the bridge collapsed. With just sections of the main span hanging over the water, the steady winds continued, taking the rest of the span 25 minutes later. This disaster hurt no one and ushered in a new era of suspension bridge design and testing.
How high were the sidewalks rising on the Tacoma Narrows Bridge as it oscillated from side to side? How high were the sidewalks rising on the bridge? The maximum height was estimated to be at 28 feet every 4 seconds.
I didn't need 3 months. I didn't even need 3 days. Oh no! Oh no! I can't believe this! Why didn't I follow his instructions? My bridge is so busted.
Of the thousands of bridges built, how many engineering design projects were unique and had never been done before? Of the thousands of bridges built, how many engineering design projects were unique and had never been done before? The answer is all of them, because each location is unique in soil type, weather, traffic needs, and material access. No two bridges' designs are exactly alike.
Hi, I'm Fidel Gonzalez. I'm a civil engineer and a licensed surveyor. I'm responsible for creating topographic maps. On my maps, I need to show the hills, the valleys, the streams, and the trees. I use this cool equipment to create my maps. This equipment uses lasers, and I also have equipment that uses satellites. I'm the most important engineer on site because the project can't get started without me.
Where's your bridge?
Okay, people, quiet down. Good morning. We're going to start viewing our projects today, which I'm very excited about. And it's Brianna's turn. Are you ready?
Well, my report is on bridges. There are many kinds of bridges. There are arch bridges and suspension bridges, and there are truss bridges. The Romans built stone bridges thousands of years ago.
Well, Brianna, weren't you going to build a popsicle bridge so that you could show us how the structure would support weight?
Yeah, I was, but I decided to do it another way. The consulting engineers who build these bridges have to use different types of materials to accomplish the same task.
Okay, go ahead.
For example, if you were to try to lift Mr. Smith's briefcase with this yardstick, you can see that it bends almost to the point of breaking, and it wouldn't take much bouncing for this bridge to break. But if you were to take the yardstick and make it in an arch and try to support the same briefcase, you can see that it holds the briefcase without a sag at all. This is called compression. Now, if you take the same yardstick and hold it this way, you can see that the yardstick holds the entire weight without a problem. Now, if you put the two together with the proper materials and a proper structure, you have a very strong bridge. also to do, and that pretty much sums up bridge technology. Class dismissed.
Whoa, 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 whoa. That's my job. Besides, we got 20 minutes left in class. It was a great report, very imaginative. Let's talk about it a little bit. First of all,
Brianna is so not busted. And even though her popsicle bridge didn't work out, she was able to use her knowledge of bridges to bail her out.
Excuse me, Mr. TV man in the back. You're interrupting my class.
Oh, I didn't think you could all right. Brianna was pretty resourceful, asking a consulting engineer to help her with her project. That's what it's like in the real world when cities and counties need help with bridges, buildings, tunnels, or even safe water. That's who they call too. If you'd like to build a popsicle bridge, like this one built by famed bridge builder John Christiansen, actually he's an 8th grader, get a pencil, here's what you'll need. 114 popsicle sticks, white glue or wood glue, rubber bands or small clamps, orthodontic bands are great, a ruler, 2 or 3 heavy books, a saw, or some sandpaper. Here's a quick explanation of how to do it, and it's easier than you might think. You're doing this in kind of a modular fashion, and what you'll do is you'll start by making 3 wide popsicle beams, and then what you'll do is you'll break some in half and glue them together first. Then you're making the beams that run across the top, and then you're going to create the wall structure, and this is actually a truss bridge, and you're going to use 2 popsicle sticks being glued here, and then you're going to put the road connected to the beams along the bottom. You'll drop the walls onto the roadway. You'll press it all down with books, of course. These are decorative popsicle sticks, and then you got yourself a bridge. If you'd like more detailed step-by-step directions for the bridge or other information about engineering, go to this website, www.discoverengineering.org. That's www.discoverengineering.org.
How much weight do you think a 1-foot-long popsicle bridge might hold?
Well, let's test this one. 10, 20, 30, 35, 40 pounds and still standing. Well, that's the end of the show, and we'll see you again next time for another adventure into the invisible world. I'm not the best spinner. I'm 3rd best. Little help with that? Little help? Little help? This program was funded by the American Consulting Engineers Council's Public Relations Committee.